This is the second in a series of videos about chemical bonds in our honors chemistry class chemical bond unit. The first video was an introduction, and here we're picking up on ionic bonding, and we'll get into some of the nitty-gritty of this. So, in simplest terms, an ionic bond is a bond that holds together ions. What is the force involved? It is the opposite attractive force between cations and anions, and we call that the electrostatic charge attraction. And once again, it's between cations, which come from metals, and anions, which come from nonmetals. Many ionic compounds are called salts. Your textbook makes a little bit of an overgeneralization about salts, but really they're obtained from a neutralization reaction. The formula unit is an important term here, and it is the simplest ratio of elements in an ionic compound. But when we take, for example, sodium chloride, a simple ionic compound, that I cannot remove just one sodium chloride. I can't have just an NaCl in isolation. It depends upon the entire large crystal lattice structure of sodium chloride. But if I was able to, in theory, pull out one NaCl bonded to each other, that would be a formula unit. It's that lowest whole number ratio. It doesn't actually exist one piece of NaCl. Once again, it depends upon the large crystalline structure. But if I did have just one piece, then I would call that piece a formula unit. It's that lowest simple ratio. So I see right here the structure of sodium chloride, and you see that I can't pull out just one sodium and one chlorine here. That if I was able to grab just one of each of these guys, pull that out, I'd call that a formula unit. But the whole structure really depends upon the entire crystal arrangement. So do molecules have formula units? And down here I see some molecules, and specifically some molecules of water. And here I have an individual H2O, an individual H2O, 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 and each one of those are separate molecules. So it does not depend upon the larger structure, and I can't have just one piece of those substances. So molecules do not have formula units. I don't need to use that term there. And molecules also do not need to be in the simplest whole number ratio. Sort of a vocabulary term that we might get into a little later is coordination number. And coordination number refers to the number of ions of opposite charge that surround an ion in its crystal structure. So, for example, if I take this chloride ion right here in this sodium chloride structure, then it would have a sodium ion above it, below it, to its left, right, in front of it, behind it. So it has a coordination number of 6. So all the sodiums and all the chlorides in the structure of sodium chloride have that same coordination number of 6. Alright, so when we show ionic bonds, that we can use electron dot diagrams to show the transfer of electrons in forming that ionic compound. And down here at the bottom as an example, I could show, here's my sodium on the left, my fluorine on the right as atoms, and this one electron from sodium will be transferred over here to fluorine, and now fluorine will have one extra electron, and it will become the fluoride ion, and sodium will have lost that one electron, so it will become the sodium cation. What type of elements are involved in these ionic bonds? As we said before, they're metals, which form the cations, and nonmetals, which form the anions. Alright, so a chemical formula like Ca3P2, once again, the subscripts did not turn out quite right, so this should be Ca3P2. What does this chemical formula show? Not to insult your intelligence, but to remind you that this 3 right here refers to the fact that in the ionic compound there's 3 calciums, and the 2 refers to the fact that there are 2 phosphide ions. So what does it show? It shows what atoms are involved, or what ions are involved in the bond, and how many of those ions there are. So the chemical formula shows the number and kinds of ions, and the formula unit is that lowest whole number ratio. that it is like one small piece of an ionic compound, which doesn't really exist in isolation, but it can be helpful to talk about just one piece. And how do we determine a chemical formula? This is really something we'll get into in our next unit when we're naming compounds, but the general rule here is that we need our entire structure to be neutral. So we'll have the same number of cations and anions as it takes to make the overall charge neutral. So we had a little practice that we did in class where we predicted the chemical formula of ionic compounds formed when the following pairs of elements combined. So if I had magnesium and oxygen coming together, and I'll just do a couple of these as an example. We did all of them together in class. Magnesium has a charge of +2, and the oxide ion has a charge of -2. So in order to make a neutral compound, I only need one of each. And my formula would be MgO for magnesium oxide. If I have something like Al and F, then aluminum as an ion has a charge of +3, fluoride as an ion has a charge of -1. So in order to be neutral, then I need 3 of these fluoride ions to balance the +3 from my aluminum. And we can show that right here, at least when we're starting off, by saying, okay, here's my aluminum with a +3 charge, and then, here's my one fluoride with a -1, a second fluoride with a -1, and a third fluoride with a -1. So together I have +3, and then -1, -2, -3. So altogether it makes it neutral. The +3 balances the -3, and I get my formula of AlF3. Alright, so when we look at the properties of ionic compounds, then my first property is that they are crystalline solids. They have relatively high melting points, and they don't tend to conduct heat and electricity, and we'll really focus on the electricity side of things. So if they are crystalline solids, what does that imply about the nature of the bonds? And it implies that those bonds are very organized and orderly. And then what happens when we apply force to these bonds? So because there's such a regular arrangement of positive and negative charges, when we apply force to a crystalline solid, then we misalign those charges, and you can get like charges lining up next to each other, which causes a strong repulsion, and it shatters that crystal, which leads to another property of ionic compounds, that they are brittle. And lattice energy we'll talk about more later, but lattice energy refers in general to the energy in that crystal lattice. And it could be discussed in several ways. One is the energy released when that lattice structure is broken apart, and we'll mostly focus on it in that direction. Alright, high melting points. So what do the high melting points and high boiling points refer to for an ionic compound? Well, when we break bonds, when we melt or when we boil an ionic compound, we are breaking the ionic bonds. We're disrupting those actual bonds. And it's an important point here because we'll compare that to what happens when we melt and boil molecules. So if you have a high melting point or a high boiling point, then you have a strong ionic bond. So in general, ionic bonds are pretty strong, and evidence of that would be their high melting points. So why do they not conduct electricity? Well, the flow of electricity is quite simply the flow of electrons. And for electrons to flow, they need a path to flow. And as I look at each of the parts of my ionic compound, it's made up of cations and anions. And each of those hold on to their electrons fairly tightly. The cations have lost their entire outer energy level. They have a fairly large effective nuclear charge from their nucleus pulling in their remaining valence electrons. So they're not letting go of what electrons they have now. They have them held fairly tightly. The anions don't hold their electrons quite as tightly, but they still hold their electrons pretty tightly. And quite simply, electricity does not flow because there's no path of mobile electrons for electricity to flow through. If we want to make an ionic compound conduct, then we have to provide the electricity with a path. And the two primary ways that is done would be, one, dissolving it in water, or two, melting it. So a molten ionic compound will conduct electricity well, and so will an ionic compound when it's dissolved in water. Which leads us to my next property. They tend to be soluble in water for the most part. What does it actually take, though, to be dissolved in water? And when something dissolves in water, then all of those ionic bonds are broken up, and each of the ions separate. They go their own way inside the water. So specifically, the attraction between the ions and water must overcome the attraction between the ions themselves. Which leads us to this concept of lattice energy. If we have a very, very high lattice energy holding those ions together very tightly inside the ionic compound, then we can get situations where it will not dissolve in water because there's too strong of an attraction to the lattice structure, and water cannot overcome that attraction and it cannot dissolve that substance. So what factors will determine the strength of an ionic bond? And our primary factors here are our charge and the size. So we have the force of this attraction is equal to a constant, which we don't really need to worry about, times my charges, which I'll call Q1 and Q2 of my two different ions, and the radius squared. So we see from this that the strength of the force of that ionic bond is directly proportional to the magnitude of the charges. So if we have ions with higher charges, like magnesium has a +2 charge, it's higher than sodium, and aluminum has a +3 charge, it's even higher. So that will lead to a stronger force of attraction because think of it as a stronger magnet inside that. Instead of weak magnets holding together the ionic compound, it's strong magnets here. So the stronger the magnets, it's directly proportional to the size of the force. Now if we look down here, the radius squared, here we're talking about the ionic radius, and that you notice that it's a squared term. So the force gets weaker very, very quickly as my ions get larger. So it gets weaker, it's inversely proportional to the square of the radius here. So if I, for example, tripled the size of my ions, then I'm going to decrease the strength of that ionic attraction by a factor of 9. So the two things that determine the strength of this bond, once again, are the charge of the ions. Stronger magnets, higher charge, will give me a stronger ionic attraction, and the size. So the smaller those ions, the greater the force of attraction, and the stronger the ionic bond. So, one more time, strong ionic bonds, we have higher charges, and we have smaller ions. And here I have some information where you can actually see the lattice energies of some different alkali metal halides at the top. And down at the bottom I have the lattice energies of some salts of hydroxide and oxide ions. So if I have a pairing of lithium and fluorine, then you notice my lattice energy here is 1036 kilojoules per mole. Now as my anions get larger and larger and larger, I'm going down the periodic table, you notice that I get a lower and lower lattice energy. And that is my R squared part of the equation, showing that the larger I get, the smaller my lattice energy. And here I'm getting larger and larger and larger for my anions, lithium down to sodium, potassium, rubidium, cesium, and I also get a decrease in my lattice energy. So my lowest lattice energy down here between cesium and iodine is smaller, even though everything up here is the same charges, +1 to -1, that this is significantly smaller than the lithium fluoride because of the radius. And down here you see that I have some really off-the-charts lattice energies. Aluminum oxide has a lattice energy of almost 16,000 kilojoules per mole. And the factors contributing to that are, well, aluminum has a charge of +3 and oxide has a charge of -2. So we have a much greater numerator here, and we know that our strength, the force here, is directly proportional to the size, the magnitude of the charges. So these are strong magnets, and they're tiny. Aluminum is an absolutely tiny cation. That it lost its entire energy level, the whole third energy level. The remaining 8 valence electrons are held with an effective nuclear charge of +13. So really, really, really tiny. An oxide only has 2 energy levels. It's not a very large ion either, and we end up with this very, very high lattice energy. How does something like this influence my melting points and my solubility? And I would expect something like aluminum oxide down here to have a very high melting point, which it does. And I would also expect this not to be soluble in water, which it is not. It's held together too tightly. Alright, so if I take a look at this term electronegativity, and we saw this in our last chapter, and this is the tendency of an element to attract electrons when it's involved in a chemical bond. It's an assessment of the strength of those elements. How strongly are you pulling on the electrons of another element? So, what type of electronegativity values would we expect to find in the elements of an ionic compound? Well, I would expect my anions to come from nonmetals which have a decently high electronegativity. They're strong enough to be able to pull very, very tightly on the electrons from my metal. So tightly, in fact, that they'll steal the electrons from the metal. So the nonmetal ends up stealing from the metal. So I expect my metal to have fairly low electronegativity values, and I expect my nonmetal to have fairly high electronegativity values. And if you look at a chart of electronegativity values, you'll see that that is. Alright, here we get into a somewhat tricky concept here, and that is ionic and covalent spectrum here. That it's not always a black and white line here between what makes something ionic and what makes something covalent. And on my pure ionic side of the spectrum here, I have something like sodium chloride. And it involves the pure stealing of electrons with no electron sharing at all. The sodium's holding on entirely very, very tightly to its electrons. The chlorine's holding on tightly to its electrons, and there's no sharing going on. With covalent here, we have pure sharing of electrons. So something like H2 would be an example of absolutely pure sharing. That the hydrogen and the hydrogen, they have the exact same strength, and they're both pulling on the electron from the other hydrogen in the same amount. But what happens is most compounds are somewhere in between. So I have H2O here, water as an example, where yes, it's covalent, but it's not very even sharing of electrons. And I have something like ALI here, ALI3, aluminum iodide, where yes, this, we might want to say it's ionic, aluminum's a metal, iodine's a nonmetal. It turns out that it's not really that ionic, and we'll get into maybe why that's not ionic. And then we see beryllium bromide here. Alright, so beryllium is pulling pretty hard on bromide's electrons, and it's not really a pure stealing going on. So let's get into some of the details on what makes up this spectrum. Alright, so when we want to be able to distinguish bond types, just as a quick reminder to everybody, metal plus nonmetal, almost always ionic. Nonmetal plus nonmetal, here we're thinking covalent molecules. Just metal atoms, we're thinking metallic bond. Random definition reminder, you might want to look back to our last section where we talked about chemical formulas and molecular formulas. Chemical formulas are just a generic term showing me the numbers and kinds of atoms, and molecular formula is the same thing, it's just applied to a molecule. Alright, so I always have such a hard time pronouncing this. I actually even have a link here to the Google Translate to hear Kazimierz Fahans or Fahans rules. Anyways, it's a Polish name, and I'm going to butcher the pronunciation of it either way. But these are rules to determine whether a chemical bond will be ionic or covalent. And we'll talk about ionic nature of something, and we'll talk about covalent nature of something. So my general theme here is that the more readily the anion can be polarized, the more covalent my resulting compound. Therefore, also, on the other side of the coin, substances that have strong polarizing agents as cations and easily polarized anions can actually be covalent, even if we're dealing with a metal and a nonmetal, because the electron cloud is so polarized that electrons are shared between the atoms, that it's no longer the stealing of electrons, it becomes the sharing of electrons. You get that full overlap of electron clouds forming molecular orbitals. All right, so on the ionic side of the spectrum, what we're looking for something that's going to be more ionic, so we're talking pure stealing here, is that my anion is not easily polarized. Its electron cloud cannot be distorted easily, and that is typically a small anion. The smaller the anion, that means it's holding its electrons tighter, so they won't be able to be polarized or distorted easily. So what makes your anions relatively small? And we want my small negative charge, and we do not want many energy levels. So the fewer the energy levels, the smaller that negative charge, then the more ionic. And so the ideal case of something like that would be something like the fluoride ion. That it is extremely difficult to polarize the fluoride ion. Only has 2 energy levels, and it only has a -1 charge, so it still has an effective nuclear charge of 7 trying to hold 8 electrons. It's really about as small as we can get for my anions. All right, on the other side of the coin, that we want a cation that can't polarize that anion very well. That it does not pull very, very hard on the electrons from the anion. So a relatively large cation would not be able to pull very hard. If we recall, what makes the cation large to begin with? Well, it's large because it's not holding its electrons very tightly. So a small positive charge or a lot of energy levels would make that happen. And things that would fit that bill really well would be things towards the bottom of group 1. Maybe my potassium ion, it's not a very strong polarizing agent. I mean, if we want to get really, really weak, we can think about something like a cesium ion, which is a very, very poor ability to polarize. All right, so let's look at the other side, the covalent side. We said what makes something very, very ionic is that the anion cannot be distorted and the cation does not do a good job distorting. That means we want a very small anion and we want a very large cation. Well, covalent is exactly the opposite. Here we would like a large anion that can be very easily polarized. And here we want a small cation that has a very strong ability to polarize. So what makes an anion relatively large? Well, we want a decently large negative charge and we want more energy levels. And it turns out that the more energy levels is much more significant in this case. So my ideal example here would be something like iodide. And iodide is way down there on the periodic table, that it has 5 energy levels, and it is probably the easiest to polarize anion out there. So often we will find situations where we're thinking of iodine as a nonmetal anion, and if we're grouped with strong enough of a cation, then it will actually become covalent rather than ionic. So we want cations, once again, that are small, have a strong ability to polarize. So what makes that cation relatively small? We're thinking large positive charge and few energy levels. And the ideal case here would be something like my aluminum ion. And boron, even though it's a metalloid, boron very, very often will form molecules as well. But really aluminum we're going to think of as our ideal metal that has the ability to form molecules, to form covalent bonds. All right, so my polarizability summary here. So factors that are affecting my polarizing power, I got the size of the cation here. So polarizing power, its ability to distort somebody else's electron cloud. So who can do a good job distorting an electron cloud? Well, all of these right here have a positive 2 charge. So the smaller you are, beryllium ion's the smallest in this group, it's the top of group 2. Beryllium ion is going to be the best at doing polarizing. And we get worse and worse as we go down, and barium would not be very good at polarizing. So the smaller that cation makes a difference. The other thing is the charge of that cation. The larger the charge means that it's going to have a much larger effective nuclear charge, and aluminum here is definitely the best at polarizing in this group. And all of these guys are going right across period 3. So the other thing that will have an influence here is the electron configuration of the cation. So this is something we did not make a very large emphasis of in class, But if we think about mercury ion versus calcium ion, they both have about the same radii, but calcium has a noble gas configuration. And if we look back to our last slide, we see that if we're not in a noble gas configuration, you do have a greater ability to polarize. All the details are a little beyond the scope of this class, but it has to do with the fact that those d electrons do not shield quite as effectively, and therefore the nucleus will have a greater pull on those valence electrons and also pull on the electrons from that anion. And that's why the non-noble gas configuration ends up having a greater polarizing ability than the noble gas configuration. Alright, so factors affecting my polarizability. Also, when we're thinking about the anion, the size of the anion matters. So polarizability, once again, talks about how easily your own electron cloud can be distorted. So if your electron cloud could be distorted very easily, then you have a high polarizability. And iodine's right at the top of that list there. It can be polarized the easiest. Everything here is in group 17, so as we go up group 17, we get smaller and smaller and smaller, so you can't be polarized as easily. The other side of the thing would be the charge of the anion. So here we have a larger charge for nitride versus oxide versus fluoride. So nitride can be polarized easier. All of those have the same electron configuration, but we have the larger nuclear charge here. The larger nuclear charge at my fluoride, so it's pulling harder on electrons. It'll be a little harder to polarize. Okay, let's take a look at a couple practice problems where we're trying to get an idea of the ionic and covalent nature of these compounds. Once again, most of these will be ionic compounds, but some of the ionic compounds will have a more covalent nature to them, meaning that one electron cloud of the anion is being distorted enough that it's pulled over towards the cation. And if it's pulled strongly enough, then we actually can get a molecule out of this. What are the implications of my anion's electron cloud being pulled over to the cation? Well, in general, that tends to make the ionic bond stronger. And we see things like higher lattice energies, we see things like higher melting points. So it does have quite a strong influence here. Alright, so let's look at this first group right here, going across. We have the same anion in all the cases, the same cation rather, sodium ion, but my anion changes and we're going straight down group 17 here. So we have fluoride at the top of group 17, and then we have my chloride and my bromide and my iodide. So if we're going from most ionic to most covalent, so the most ionic would be involving the anion that cannot be distorted very well. And so which one of those anions cannot be distorted well? Well, this is the top contender right here. That would be by far the most ionic. That fluoride ion is very, very difficult to polarize. And then we would go, so this would be my most ionic, second most ionic, third most, and fourth most. With my next trend here, we have the same anion, the bromide anion. And all we're changing here are my cations. So all of these cations are in group 1 of the periodic table. So the most ionic would be the cation that does not do a very good job polarizing. That is not going to distort that electron cloud of the anion. And the worst one at that would be my rubidium here. It's the largest one, so it would be the most ionic. It does the worst job polarizing. And then as I go up my list, then my potassium would be next, and then my sodium, and finally my lithium, which is the smallest cation there. Alright, we did the rest of these examples in class, but for the purposes of making this video a little shorter, we'll keep moving now. Alright, here I just had a little interesting information that I thought showing some different ionic compounds and their associated melting points. The format got a little distorted as I converted from OpenOffice over to an Office document, but right here I have AlF3, and this is the crystal lattice structure of aluminum fluoride. And you see that it has a decently high melting point of about 1200 degrees Celsius. As I go from aluminum fluoride to aluminum oxide, you see a big jump in the melting point. from 1200 up to 2000 degrees. So the question is why? Why do we get such a big jump? We're just moving over one spot on the periodic table, from fluorine to oxygen. And my answer here has to do with the force of the ionic bond, that I go from having a sum total of my forces here of 3 and 1 to 3 and 2. So I literally double the product of my forces. I go from 3 times 1 giving me 3 to 3 times 2 giving me 6. So I double the strength of my bond. And there's not a very big size difference between fluoride and oxide. So you're not going to decrease the strength very much with size. And over here I see the structure of aluminum fluoride. Would I say that's more ionic or covalent? And aluminum oxide would be more covalent because that oxide could be polarized a little bit more. All right, and then I get even a little bit more covalent with my aluminum nitride, and I get much larger charges. Here I have a +3 and -3. So my product here is 9 of the charges, and you get quite a bit stronger, and I get another increase there in my melting point for aluminum nitride. And this is aluminum nitride. All right, my next structure over here is lithium chloride, and there my melting point is 605 degrees Celsius. So you get a fairly big drop. So let's look at why that might be. Well, my anion is relatively difficult to polarize. And my cation, it's a small cation, but there are better polarizing agents out there. Particularly, I'm thinking about things like lithium, or even beryllium would be a better polarizing agent. And my charges are only +1 and -1, so you don't have a very, very large charge to help the force of your ionic bond. So I don't get a very, very high melting point. Beryllium chloride. So I'm just switching up my cation here, and I get a stronger cation. It's a better polarizing agent. It does a better job distorting chlorine's electron cloud. And it ends up distorting it enough that I get almost molecules here. They end up looking like chains, and all I have to do to melt this is separate one of these chains from the other. So it's a much easier force than breaking up a whole crystal lattice. And you see that great drop in your melting point as well. And then finally I go to boron trichloride. So I'm just moving over my cation once again here, and now the boron is such a good polarizing agent. It's absolutely tiny that it really distorts this chloride's electron cloud so much that it becomes a molecule. And look at how that melting point absolutely plummeted way down there to negative 107 degrees Celsius. So you can get stronger and stronger with a highly covalent ionic bond like aluminum nitride here, but it is a huge melting point there because it's still a crystal structure that we see. But if it drops enough, and that polarizing agent gets strong enough, and my anion can be distorted enough, then I actually get molecules and a huge drop in melting point. All right, this is a little question we had in class. Explain why aluminum phosphide has a melting point way up there, 2500 degrees Celsius, but aluminum chloride has a melting point of 100 degrees Celsius. So aluminum chloride versus aluminum phosphide. The only thing I'm changing here is my anion. So why the big difference from phosphide to chloride? And we actually would think, all right, well, phosphide's larger than chloride. Therefore, phosphide should have a greater polarizability, and therefore it should be more covalent. Maybe so covalent we would be thinking aluminum phosphide, hey, it's probably a molecule. But it turns out, no way, that's not a molecule. Look at its melting point. So, however, evidence seems to suggest that aluminum chloride exists as a molecule and aluminum phosphide exists as an ionic compound. So what's going on here? And this brings us as a reminder, what are the things that affect the strength of that ionic bond? And I have my charges and the size of the ions. And in this case, the big difference here is the charge. My phosphide has a charge of -3. Aluminum has a charge of +3. So we get a sum total here, my product of the charges is 9, versus if I'm comparing aluminum and chloride, it's only 3. So that ionic bond is strong enough that, I mean, even though phosphides can be polarized a little easier, that charge overcomes it. And it's going to hold that aluminum and phosphide together so strongly that we get this huge melting point. Alright, so that's where we're going to end our second video on ionic bonds, and we'll pick up for our next one discussing covalent bonds.